So, hello everyone. I'm Betty Hurley-Dasgupta, and I have with me Carol Yeager, and we're the co-facilitators of VizMath, a MOOC. And just a few reminders before we get to our guest speaker today. One, be sure to use Twitter and use the hashtag VizMath to get our community together of talking about things that excite us about mathematics. Also, those of you who are registered, if you're not, please register, but those of you who are registered, please also register your blog, and in your blog put in the hashtag VizMath for things that you want to show up in the daily report. And also, one of the participants, Omar, has started a Facebook group. It's called VizMath:/a MOOC, and if you just search for VizMath, it should come up, and please join that growing group. So I'm now very pleased to introduce our speaker today, Daina Taimina. I'm sorry, I probably messed up your name, so please say your name when you come on. And have her also tell you a bit about herself as she gets started. And thank you for being with us today.
Thank you, Betty, and hello, everybody. My name is Daina, Taimina. Betty, you had it pretty close. And I'm used to that people are confused. I'm Latvian, and that is a Latvian name, so therefore that is something hard for people to know. Not many people speak Latvian worldwide, but still there are some 2 million. Okay, well, I want you to just tell my story, which if you watch my past presentations, and that's on that, so that you know, like, I was a mathematician, and in school I was told that I am somebody who can't do art, so I did math. And now somehow, for a surprise for myself, from a mathematician, I have become an artist. So I had to learn to be an artist. In other words, I can say I had to learn to become somebody I thought I will never be. Well, okay. So, sorry. Well, this is one of my things, and when people sometimes give me a compliment, and thank you for the compliment, that they like that I'm picturing my pieces in a nature. So I must say that I live in Ithaca, New York, and it's a very nice area to have these pictures in the nature, and also I'm taking advantage of sunny weather and nice background, so I will continue. But since we are talking about visualizing mathematics, of course you will have a question. So what essentially it is, and if I was saying that this is a hyperbolic plane, that everybody knows. And apologize if you have seen already these TED Talks and you have seen these slides, but there is always somebody who had never seen that or just start conversation. I will just quickly run through. So excuse me if I'm too fast, but you can always go to some other recordings and see it, and later we'll have a chance to ask me questions. Okay, so let's move to the math. What is the hyperbolic plane? Before I start, usually I put it up, this warning, which Wolfgang Boyer, who was the father of Janusz Boyer, one of the starters of this new type of geometry, one of the non-Euclidean geometries, which later got the name hyperbolic geometry, Janusz Boyer. So the father who was also thinking about this possibility of a new geometry, and he was actually the classmate of Carl Friedrich Gauss. And Gauss was the greatest mathematician of the 19th century and sometimes called the king of mathematics. So he knew that this is something very can really consume all your time. So this was a warning father gave to the son. Son didn't listen and came up with his ideas, and that's very nice. So independently, of course, this hyperbolic geometry was also discovered in Russia by a Russian mathematician Nikolai Lobachevsky. But for a long time, it was just theoretical, and there wasn't any particular models. And of course, when you try somebody to tell theories, not everybody can imagine that. And it was very nice that in 1868, Italian mathematician Beltrami came up with the idea how this hyperbolic plane on which hyperbolic geometry can be executed, how this hyperbolic plane exists. If you know my book, then there is not this picture, because this is a photo I received after already book was published, and this is an original paper plane done by Beltrami. I was really stunned seeing the resemblance to my work and what I'm doing, and so how he had made it, and he called it a pseudosphere. Pseudosphere because when you wrap it, so then it's looking something like that. And since this is an old paper and this is in archives of University of Padua, these photos were kindly provided me by Piero Odifredi, who took them for his book. So then, of course, you can't really make it very tight, but if you do it tight, then you come up with something like that. And this is by the end of 19th century and the beginning of the 20th century. These were gypsum models, which were, or clay, sometimes clay models, which were used in many classrooms around the world. And as you see, this comes as a Life magazine, and if anybody knows which issue of Life magazine this was, please let me know, because I have been unsuccessful so far to find which one it is. I'm trying to find it. Pseudosphere, as Beltrami called it, and his name came in. It's from a physical point of view, from physics, it can be a loudspeaker. So then, before the electronics and other loudspeakers which we're using right now and amplifiers, this was used for the first record players, and also it was used as a shape for a loudspeaker, and it's really the best shape for a sound without any other mechanical means. So this part is very nice because, well, we can see it also in the nature. There are some flowers which grow like that, but that the surface of the pseudosphere is the surface of revolution, which is coming out of a so-called, from a curve which is called tractrix. And so then this so rotating it, we could get, this is a computer can draw it like this, and essentially to draw a very precise model of hyperbolic planes, computers can't go much further like that, and that would be kind of in some ways a paradox, because I received my PhD in computer science, and now I could share something which computer can't simulate. So why computer can't do it is because already in so this is the one, some already thought, there were some thoughts about it. The pseudosphere might be a shape of a universe. Well, this idea proved wrong. But David Hilbert in 1900, so he said that that can't exist because we would need a fourth dimension, so that we would need do the embedding. Well, there is a much more mathematically precise definition of that, but let's skip. Essentially what came out is, in simple words talking, that we can't have a simple formula for a hyperbolic plane to describe it like with algebraic equation. So what I mean by that is that perhaps you remember from school, we can say that the circle can be written as x squared plus y squared equals r squared, or if we are adding another variable, x squared plus y squared plus z squared equals r squared, so then we are getting a sphere. Similar formula can be written for a hyperbolic plane, and that is due to the Hilbert's theorem. So therefore, the mathematicians for a long time thought that it's not really possible, and eventually there was some decline in interest on that. Well, I was skipping lots of history. In 1970s, Bill Thurston started his interest and essentially talking about these hyperbolic manifolds and three so-called three manifolds, and he didn't know about the Beltrami's model made out of paper. A person came out with his own idea how to make it, and as you see, this was built by some teachers in some teachers' workshop. And this is the plane which I saw in 1997 when I was supposed to start teaching hyperbolic geometry in university, in Cornell University. And then I was looking at this and I said, okay, visually this gives a pretty nice idea what it is. But of course you can see this visually, but you can't really use it. And I was very much wanting to be able to fold it and to do something with it and to give a chance for my students to touch it. So I was thinking that, okay, I'm not going to make these planes, these paper planes, like for each lecture, you know, like the women are treasuring their time, and thought I should be able, if it's possible to do it out of papers, and I should be able to crochet. Well, so how did I do it? There is this question. So then I had been asked the question, when this aha moment came? Well, this is it. This is what you are seeing right here. Because there is an exponential growth embedded in hyperbolic plane, because there are distances which are growing exponentially. So I was thinking, well, how I can help people to visualize exponential growth. And then I remembered about like the thing, how rumors spread, that if we just tell one more people, so you see that we are getting these powers of 2. And when I draw this, so it looks like a graph. Mathematician says this is a graph, but suddenly it kicks in my craft side, which was so far as a hobby, and I said, oh, wait a minute. This is how we are drawing pictures, how to crochet. So well, then we can crochet. So this is really, so this is nice, but it would be really very crunchy to do it. So I tried a little bit slow it down. As you see that its previous one was, if you pay attention to this, this is a previous one was y equals 2 to the x. Slowing it down means that I'm not raising 2 to the x, but just getting less than 2. So the less than 2 would be 3 halves, as you see there. So what does it mean as for crocheter is that I crochet 2 and do increase in a 3rd stitch. Well, I should have known as a mathematician better that it will be growing pretty fast too. So my first came out like a so this crunchy. So yeah, so some scrunchy would be like this. Well, so I decided it needs to be slowed down more because I wanted to make a pictures of them. And so well, when you get closer to the one, like here, this is 12 over 11. So it means I crochet 11 and do increase into the 12th stitch. As you see that as when this ratio approaches 1, then it gets like sort of like a flat. And mathematically speaking, if it is 1, then we are getting Euclidean plane. That is the same paradox which is happening with a sphere. If we are having a sphere with a small radius, let's say you're having a sphere with like radius 2 inches, you can hold this ball in your hands. When it is like 2 yards, its radius is 2 yards, it's getting big. And when it's 2 miles, then you won't experience it anymore as a sphere, but now it's getting closer to the Euclidean plane. So there is this middle, yeah, so this golden middle way. So therefore, that is what I was doing with a hyperbolic plane. Now, once I had some surface on which I can make pictures, so then I decided I can make a picture. And then this is a picture. So well, what it is that Euclid's first postulate, which is like in a very simple talking. Like if we are having a line in on a plane and we have a point outside, then in Euclidean plane, or that is on your tabletop, what we can do is, all we can do is just to draw one line through the point outside the line, which is parallel to the given one. While on hyperbolic plane, it's possible to draw through the point, which in this picture it is that middle point where these three straight lines intersect, and they are all parallel to this lowest yellow one. Well, something totally different than it was in the Euclidean plane. How do you get straight line on hyperbolic plane is the same way like we would do in a piece of paper. You just fold it. And once it's folded, then you can just make these, lines. So one way to think about it is, imagine that this is your white sheet of paper, which would represent Euclidean geometry. Spherical geometry would be represented with a half orange, just like outside, right? So orange peel. And then this hyperbolic plane is crocheted, the blue thing. And now you try to flatten these two to get onto this piece of paper. Well, when we flatten the orange, and you can try it, so then you can see that this orange peel is splitting because there is not enough surface to cover the same area on hyperbolic plane. Yeah, so it's less surface on a sphere, while hyperbolic plane is getting very scrunchy, so there are many folds. There is like too much surface area. And this too much, this is why it's called hyperbolic plane. Because sometimes people ask me, where are the hyperbolas on hyperbolic plane? Well, there are no hyperbolas on hyperbolic plane. The name hyperbolic plane was given by Felix Klein in 1870, and that's exactly based on the fact that there is too much surface area. So there is like the too much comparing with. And hyperbola in this sense, like we would say hyperbola also in a poetry, or something similar like that. Well, the other way how we can explain the different curvatures, essentially what we are talking about is now, we are talking about like surfaces with different curvatures. And what is curvature is that Euclidean plane is flat, spherical surface is the surface with a constant positive curvature. Imagine that you are having these hexagons, and then you are gluing them together, so so that there is a hole of a pentagon in between. That's how the soccer balls used to be. So because now you can see that if you blow up your paper model, then you are seeing this, that it's eventually approximates sphere. So this is what the constant positive curvature means. There can be also the different tilings too. I'm using this one because if you are having just a hexagons, then you can tile a floor, and that would be a Euclidean plane. It's just like flat, and there is nothing curved. But having like one out and making it in a pentagon, so that's where you're getting the curve. And for the surfaces of a constant curvature, what happens is that those are always closed on themselves. So well, this is also, you can see that this is used somewhere in architecture, and there are some other examples you can see too. So these are like very approachable and useful. While if we are taking now this middle hexagon out of flat Euclidean tiling and putting in this red polygon, which is with 7 sides, which is called hexagon, then we are getting something which is called hyperbolic plane, because now you see we are getting too much curvature. And hyperbolic plane, that's because it's infinite too. So therefore we can infinitely continue this surface. And this is a surface with constant negative curvature. I try to crochet too, since now I need to tie it with a craft, and I was like trying to explain recently the children in a Waldorf school, so therefore they got this one, because you can make these. This is a very popular crochet pattern, and you can really easily make it from hexagon to pentagon and septagon. You can see those red flowers, those are hexagons, and if you do only 5 leaves, you get a pentagon, and then you just make it like a spherical. And then if you do 7 leaves, which is this middle one, not with color but uncolored, so the same, this beige pattern. So those are heptagons, and then we are getting hyperbolic plane. Well, this is those are famous examples are the talk between mathematician Coxeter and artist Escher. Escher wanted to show how can we get this whole world around us into the circle, and Coxeter told him about the Poincare disk model, which is another representation of hyperbolic planes. That would be kind of like a map of hyperbolic plane. And then Escher came up with his famous stylings, and there are a couple more of the Escher's pictures. And we can see this negative curvature also in nature. It is now in a popular culture very much like saying everything which is ruffles, and that is hyperbolic plane. No, this is not hyperbolic plane. This is negative curvature. And why it's not hyperbolic plane? Because for hyperbolic plane we need that it's the same everywhere. So it means that this curvature of the surface is the same everywhere. Like for these leaves, we see that it's much crunchier at the edge of the leaf, but it's more flat getting towards the center. So therefore this is a negative curvature, negatively curved surface, but it's not a hyperbolic plane. So well, this is a little bit closer to that, but so you know that's kind of like more uniformly. And there are many sea creatures, of course, too, which are taking the shapes, the negatively curved shapes. And why it is, some biologists explained to me that all creatures which are getting the light or nutrition through the surface area, so then they are tending to have a maximum surface area in a minimum volume. So therefore, this is how it works, and this is how nature very nicely adapted, and that's why they are doing. At the same time, you can see there are other sea creatures, and not all sea creatures are taking exactly these negatively curved shapes. So there are much too much. So the nature has lots and lots of ideas. So this is something that I was looking for creatures, more creatures who are taking these negatively shaped surfaces. I came up with Nudibranchia, and those are biologists told me, and then I came up with these, I found these pictures which are not mine, but I was like so amazed about these beautiful colors, and I know that one of these pictures is also in my book, because I really wanted to popularize the guy who is doing these pictures on the water. And you can see what they are doing. They are doing the same thing I was doing with my planes, because on the top part, you see this is the Nudibranchia when she opens up and wants to get the nutrition or light or whatever. And then when it wants to hide, then it just rolls. So well, and that is the same thing I'm doing with my planes. So when this one is opened up, so it can be like similar like the first slide you saw today in the talk, and then I can roll it up. And when it's rolled up, then you don't understand which is a top and which is a bottom, because by the way, this is one side and this is the other side. So therefore that's how they nicely can change, and that happens if you are having really the same curvature everywhere. So if you want really to make these shapes being more mathematical, so then you keep your crocheting this increase ratio the same all the time. And so well, and I started to follow like these clues from nature, and I did something more. And you can see that I can fold the plane and get 2 holes, and then I can get 3 holes, and I can get 4 holes. But if I would unravel these, all these shapes are the same. What it is, those are what is called like geometric manifolds. And like a totally very short intro, which is Like what is one manifold? It's a circle and closed curve. This is like geometrically the same thing because you can see I can make a curve into the circle, then I can bend it, and then it is the same. Well, this is an example of geometric two-manifolds. Therefore, if you are having a sheet of paper, you roll into the cylinder, and you don't change really the surface. So it means the geometry doesn't change. That's what it is. So this is an area which is geometric topology. In topology, you can do stretching. In geometric topology, you don't do stretching because you want to keep the surface the same. And this is what Bill Thurston was talking about. And so he was my great inspiration, and I was like really heartbroken when he passed away in August. And these are only the surfaces with constant curvature can be geometric two manifolds. This is one of my works, which later you will see it's finished. So that when it was in a progress, then you can see the ball represents this constant positive curvature. Then there is a hyperbolic plane, which is constant negative curvature, and of course they are lying on a floor, which is Euclidean or zero curvature. So there is a stop sign. So if you are looking at the stop sign, now if you are in a topology, then you can follow this stop sign, gluing together every other side. Then if it's from rubber, then you can stretch, and then you end up with something which is called two-hole torus, or a pretzel, if you wish. But so this animation was done by Professor Doug Denham, and then you can see that this really destroys the surface itself. Now, if I crochet on a hyperbolic plane, I can make an octagon, and that is a special octagon which has the 45-degree angles, which is totally impossible to do it. So this is when there are when you are attaching now these ones, like when we are attaching where these velcros are, then essentially we come with a shape which is known as hyperbolic pair of fans. And hyperbolic pair of fans is nothing actually you can wear, because at the end you can attach these 2 points, and then if we would have a 4th dimension, then we can glue together these 4 holes, which you can see on this bottom right picture, which is a blue one, and then it would become also this two-hole torus or a pretzel. But then the surface wouldn't be destroyed. That would be the same hyperbolic plane, and therefore it would hold the hyperbolic geometry. Well, by crocheting inspired also some others to try to do the visualizing, and this is Kim Kelsing and Ben Kraskov and their famous Lorentz manifold. That was at the time when they were visiting Cornell Math Department, so we finally met, and it was like we were just really now good friends. Romanian designer devoted me this. He came up with an idea that maybe we can make a hyperbolic chair. So, well, I was hoping to start the mathematical fashion line, like I crocheted hyperbolic skirt, and I must say it takes about three months to do it, and my fashion didn't take off. But if you know about Isaki Miyake house and Dai Fujiwara, so he designed together with Bill Thurston, and they made 3 manifolds. They made 2 for a Paris Fashion Week 2 years ago. So this was my first art exhibit. When I was like really in 2005, I was really shocked that somebody calls me and says, "Oh, you know, like I want your works for an art exhibit." And I was like, "Oh yes, okay." And then I thought, "Oh my God, but those are all mathematical models. How can I send them to the art exhibit?" So I had to do something. So I went to the local yarn store, and this is when I came up with these. They had this nice narrow yarn, and so I just came up with these things. So, and then eventually my models traveled to Italy. So these are some art models, and so this is the one which I did for American Institute for Physics. And this was really done by, so I thought, well, since it's an institute for physics, I should do an experiment. And then my experiment was that I had these 4 shades of purple, and I measured exactly 100 meters. Each of this, each yarn of this shade is 100 meters, so therefore I call this 4 by 100. And so it means that all these areas are the same, and the length of the yarn, if I say 4 by 100, I used to be a sprinter, so then you know that there is the track field. So the track around the football field is 400 meters. So that if you would unravel, so then we can make exactly that track length. And so, well, and here is the finished one when I showed you the work in progress. So this is this is called day and night, because you can see how they kind of like my purple and turquoise ones, they just change. So I can see I'm talking like too much, not letting you time. So I tried, I'm just running through these as a picture. So this is, I tried manila reel. And just one more thing is that this is the one which got into the Guinness World Record book. So if you are going to 2013 on page 198, you can find this one. And these are some of my geometric manifolds. And these series, plus another series, are now, I just learned that I will be doing a show next year together with my friend. So, well, and all my adventures are in my book. And if you are not familiar, just try to get it in a library. So, well, and now I should let you. And so this is just like thank you, and I will let you ask me questions. Thank you for listening.
Thank you so much, Daina. That was wonderful, and I can't believe you actually answered my question as you were talking through the slides. We do want to welcome, and we had some join us after you started. We do have St. Anne's Math Art Class that you mentioned. They may be joining us, so a shout out to them. In addition, some of our faculty, Marge Robeson and Mark Marino, and Beverly West just joined us a few minutes ago. Are there questions from the group? We'll take a couple of questions. We actually have plenty of time to engage with Daina on whatever topic you want to. And I'll take one question, and then maybe I'll, because we are recording this, we'll take one question and then see if we stop the recording and continue with more questions. So you can go ahead and type your question in the chat area. Also, if you do have a headset, you can talk, and so if you do want to use your headset, to go ahead and raise your hand, and you do that by raising your hand right here. Carol, go ahead.
Hi, Daina again. I'm more of the artist rather than the math person, but I certainly have done a lot of knitting and crocheting. And my biggest question to you is, how do you keep track of all of your increases, and how do you hold this piece as you're continuing to crochet it?
Okay, so well, it's keeping track is pretty mechanical. You know, like you crochet. Let's see this piece which is now on. You crochet 7s, increase in 8. Crochet 7s, increase in 8. That's all the track you need. So therefore, I can say that I am measuring my pieces by movies. How many movies? Usually I can just do one movie and then my arm is tired. So, you know, I just measure the time by movies, how many movies I have seen. So, but how do I keep them? So this big one, this blue one which you are seeing, that one is, this is starting to get on my lap quite big. So this largest one, which is in a Guinness World Record book, I had to put it on a counter. I couldn't do it anymore watching a movie. I really had to put it on a counter, and it was getting too heavy.
great, and thank you. We just see a note from Justin saying the class had ended, but they really enjoyed your presentation, Daina. I'm going to go ahead and shut off the recording so that we can just continue more informally, and then we have a nice length recording for people to watch.